So yeah, I'm going to be going over how we enhanced the state-of-the-art CNN inference accelerator called HPIPE to take advantage of some AI optimized FPGA, which has these tensor blocks that we can use that have a ton of multipliers, but also a ton of input restrictions. So I'll start off with a bit of background info first. So convolutional neural networks are used for a variety of computer vision tasks, typically things like facial recognition or self-driving cars, but some more niche applications include things like galaxy classification or automated fruit farming. The core of the CNN is a convolution operation shown here on the right, where we take a 3D filter or set of weights and we multiply it against a set of activations. In this case, the activations have red, green, and blue color channels to make up a color image. So the activations are either the input to the CNN or the results from the previous layer. And then so we do this multiplication, accumulate all the results, and that's how we form one output. We repeat this for the input width and the input height to form one output channel. And we repeat this with multiple filters to form multiple output channels. And so CNNs typically have billions of these multiply accumulate operations. And so these operations are parallel and friendly to low precision. One other type of convolution I forgot to mention earlier, which we'll cover in this presentation, is a depthwise convolution. So a depthwise convolution, we don't accumulate across the input channels shown here. And so each filter is essentially has a depth of 1, and we're not accumulating across the input channels such that the number of output channels is the same as the number of input channels. And so this will become important later on in our design. And so these multiply accumulates, since they're parallel and friendly to low precision, we can use FPGAs for custom hardware acceleration. FPGAs are rapidly configurable and easy to tailor for specific networks, meaning they're a lot faster to deploy than something like an ASIC, for example. They're also a lot more power efficient compared to GPUs, and they're customizable as well, meaning we can optimize them for low precision data types or special data types. So just to provide a brief background on CNN inference acceleration for FPGAs. So classically, it's been arrays of processing elements similar to a GPU. So in this case, we have our neural network here on the left, and we're accelerating one layer at a time over an array of heterogeneous processing elements shown here on the FPGA. Occasionally, we might have some more specialized units. In this case, we have a unit for activation functions, as it'll be a lot faster than a more generalized processing element. But overall, since we're running one layer at a time, this means we have less compute. And since the processing elements are generalized for any layer, we also have lower efficiency. But this is a lot more versatile, especially since it's a lot easier to use off-chip memory in this sort of accelerator, so we can support much larger networks than the alternative. The alternative being a pipeline of specialized functional units. So this is a data flow accelerator. And then here, we essentially have one or more specialized processing elements for each layer in the neural network, and we're running every single layer at once. So with each of these specialized processing elements, we use on-chip memory. You could certainly use off-chip memory, but it's a lot harder to do, as since you're running everything at once, it's not as clear what we can store in off-chip memory in order not to stall the computation. And so with this type of accelerator, we have higher efficiency and more compute. And since it can be heavily pipelined, it is well suited for FPGAs. Downside being all network parameters must fit on chip unless you can figure out a way to transfer some elements off chip while not stalling the different processing elements. And another downside is the fact that you need to create a custom accelerator for every single neural network you want to accelerate. So there's no reuse here. You have to reprogram the FPGA and recompile everything. HPIPE is a data flow accelerator, which we build upon in this work. So you may have heard about it from previous Crossroad seminars, but I'm just going to provide an overview here in case you're not familiar. So HPIPE generates custom hardware for every layer. It's layer pipelined, meaning we don't have to wait for the previous layer to complete before starting the computation on the next layer. And it has a deep configurable pipeline, meaning we achieve a high Fmax of up to 580 megahertz on some designs. We support sparsity in the form of zero weight skipping. And so we don't store any weights that are close to or equal to zero, and we don't perform any computations with these weights either. We store all parameters on chip, and we have custom precision per layer in the form of 16-bit fixed point in the baseline design. And so the number of sign, integer, and fractional bits can vary per layer. So we vary these bits in order to achieve the maximum accuracy possible. We achieve a high performance. So at the time the original work was published, we were 9 times faster than Microsoft Brainwave and 3.5 times faster than the NVIDIA V100 AI-optimized GPU. So HPIPE is a software compiler, essentially. So I've outlined it here in the box. So what our compiler does is it takes the TensorFlow graph, which is a PB file. It optimizes this graph, so it removes any nodes that might only be used for training. It merges certain nodes in the graph, reorganizes some nodes if it works better in hardware, etc. And then we take the target FPGA specs and combine this with the optimized graph by allocating resources and increasing parallelism. So how this works is we take the slowest layer and then we increase the number of multipliers in that layer so it can run faster and perform. So it can perform more computations in parallel and run faster. And we keep repeating this process until we run out of multipliers on the FPGA. So in this case, we run out of DSP blocks in the baseline design. Once we have all those numbers, we can create our hardware graph in Python. And then based off of this graph, we can generate RTL in the form of Verilog files and memory initialization files. And then these files can be compiled in Quartus and then deployed on the FPGA. So currently we target the Stratix 10 line of FPGAs from Intel. Some prior work on HPIPE, which was presented by Mohammed Ibrahim in a seminar earlier this year, is the multi-chip performance work. So what he found was that he had linear scaling with more resources and negligible communication overhead. So going from one FPGA, for example, to 2 FPGAs and MobileNet v2, he found that the latency and throughput improved by about 2x, which is what we'd expect. And so you can find more information about this in Mohammed Ibrahim's thesis if you're interested. Now, in this work, we take advantage of the AI-optimized Stratix 10-NX. And so how this differs from a regular FPGA is instead of having these standard DSP blocks, which feature just 2 18-bit multipliers as shown here, we instead have a tensor block, which takes up about the same amount of area on chip as a DSP block, but it has 30 8-bit multipliers. So creating these smaller multipliers in hardware is relatively cheap, but all the extra inputs and outputs, the programmable routing we would need to use these multipliers in the same way as a DSP block are very expensive. And so what this results in is data restrictions on the multiplier inputs and outputs. And so the question becomes, how can we reorganize computations to fully exploit this? Well, there's a couple different modes we can take advantage of. The first is scalar mode. So scalar mode has the least amount of input and output restrictions. So it's similar to a DSP. We can have 3 independent multipliers and produce 3 independent outputs, but we're only using 10% of the multipliers in tensor blocks. We're using 3 out of 30. Vector mode has more restrictions, but we double the multipliers compared to scalar mode. So 6 total multipliers, but now we must accumulate the results of those multipliers, and we can only produce 1 output. Then in tensor mode, we can use all 30 multipliers, but we also have the most restrictions on the inputs and outputs. So we operate in vectors of 10 values. And so 3 of these vectors have to be preloaded into a set of registers before we can do any sort of computations. Once we've preloaded these vectors, we broadcast in 1 vector against all 3 preloaded vectors into the dot product engines. Each dot product engine does 10 multiplications, and then the results of those multiplications are accumulated in order to produce 3 separate outputs as shown here. And so that's all the background info. So now to provide an outline of the contributions of this work. So we'll start off with the baseline HPIPE architecture, and then we'll go into some HPIPE architectural improvements. So I'll cover these in more detail on the coming slides, but these were sort of necessary to implement before we could create our Stratix 10-NX implementation. We then implemented a sparse convolution engine. So this integrated with the existing hardware, and we'll cover how we implemented regular convolutions versus Depthwise convolutions. Then for the dense convolution engine, which utilizes tensor mode, so this one uses vector mode and scalar mode. This one uses tensor mode. For this convolution engine, we needed to create a whole new module. And so for that, we did a compute and memory organizational study before creating the dense convolution engine shown here. And so we'll cover each one of these contributions in this presentation. So starting off with the baseline HPIPE architecture, just to provide an overview of how the convolution engine itself works. So in this example on the left here, we have a set of input activations here. So these input activations are 8 by 8 with 10 input channels, which will be important later. We're multiplying them against 3 separate filters or sets of weights. These also have 10 input channels to match the input. And here we're producing an output that's 6 by 6 with 3 output channels. And so there's 3 different types of parallelism we could take advantage of here to generate the convolution engines on the right, which I'll go over shortly. The first is output channel parallelism. So this controls how many of these filters we're multiplying in parallel. So we could do one at a time, or we could multiply all 3 in parallel. To multiply all 3 in parallel, we would have to essentially create 3 copies of the convolution engine. And so each one of these colored blocks here is its own convolution engine. And we're sending identical activations to each one. So these activations are sent to each one, but each one of these stores a different set of weights and produces a different set of outputs. Output with parallelism is built in. So this is not a tunable parameter like input channel parallelism. And for this, HPIPE computes an entire output row at once. And so for what this means is we instantiate 6 dot product engines here. Each computes a value in the output row shown here. Input channel parallelism is a tunable parameter we can change. So in this case, it can go up to 10. So this is how many input channels we multiply against the filter in parallel. And so to implement this, we essentially create a chain of DSP blocks. And so inside each dot product engine, we have this DSP chain. A DSP chain is in a column on the FPGA and has dedicated routing in between DSP blocks. And so to maximize this parallelism for this example, we would need 5 DSP blocks for a total of 10 multipliers, and we would cascade the values down the chain, adding them, and then accumulating them in the last block before outputting them. And so the data flow here, we take our input activations, so the results from the previous layer, send them to the activation buffer. Once we have enough values stored here, we can start the convolution. So we steer these values into the dot product engine, as well as the weights. All this takes sparsity into account, so there's a bunch of muxes here to implement sparsity. And then our dot product engines will implement the convolution. They're controlled by a bunch of controllers that check when we're finished the convolution operation, and then we output the activations. So next, jumping into some architectural improvements we made to this convolution engine and HPIPE as a whole before implementing our design on the Stratix 10NX. So the most important of these changes is 8-bit quantization. So our original HPIPE design was essentially tailored for 16-bit values. It could theoretically support 8-bit values, but not without a major accuracy drop. And then so one of the main things we implemented here was 8-bit training, as we found that quantizing directly from a 16-bit train network produced some major accuracy drops that couldn't really be fixed in hardware alone. And so how we did the 8-bit training was we modified some existing TensorFlow quantization nodes. And so by default, these quantization nodes support uneven ranges of, say, -2 to 12, but we have to constrain these ranges to powers of 2 that are equal in size, so -8 to 8, for example. The reason for this is, so these more advanced quantization strategies mean that we can certainly store the values as 8-bit in memory, but when we're loading the values from memory, they end up being larger than 8 bits for the convolution operation. And so we can't map these to the tensor blocks, which take in 8-bit values. And so we're limited by this constraint shown here. We also made some changes to the HPIPE quantizer itself. So we run multiple images through our neural network before generating any hardware to determine the number of integer bits that we need to use for each layer. And this is to make sure we're not sort of saturating or clipping too many values. So we can represent the full range of values that we need to in each layer. That being said, if we have, let's say, 1 or 2 larger values in each layer out of 100,000, for example, it might be worth it to move some of the integer bits to fractional bits if it improves accuracy, even if it means just those couple of values end up saturating. And so with all these changes on the right here, we have the results shown in this graph. So here we have TensorFlow 16-bit and FPGA 16-bit, and then TensorFlow 8-bit and FPGA 8-bit shown here. And so we have a bit of a drop going from the TensorFlow 16-bit to TensorFlow 8-bit, but the biggest drop comes from TensorFlow 8-bit to FPGA 8-bit, especially for MobileNet v3. And this is because of another limitation in the TensorFlow quantization strategy. So by default, TensorFlow only inserts quantization nodes before each convolution, but the convolution itself is done in 32-bit floating point. And so this is different from the FPGA, where our entire bus and all our multipliers are in 8-bit. And so to reduce this accuracy drop, we'd have to update the TensorFlow quantization strategy to more accurately match what's going on the FPGA. Some other architectural improvements which we needed to implement. So Depthwise convolutions did not support any sort of parallelism in our baseline design. And this is because they were not the limiting layer for most networks except for MobileNet v2. But on the NX, we want to reach some higher parallelism settings. We want to use more multipliers. And so these Depthwise convolution layers quickly became the bottleneck for most networks. And so we had to implement output channel parallelism support for Depthwise convolutions. There's no input channel parallelism support, as for Depthwise convolutions, each input channel or each filter has a depth of 1, essentially. But with output channel parallelism support, this increased MobileNet v2 performance in the baseline design, and also allowed us to use the multipliers in the on the Stratix 10 NX. We also implemented support for some additional networks, because larger networks like Resnet 50 do not fit on the NX due to memory limitations, and so we expanded support to include MobileNet v3 instead of Resnet 50, just to have more variety there. So next, jumping into the sparse convolution engine. So recall that this convolution engine sort of integrates with our existing convolution engine, and so we didn't need to really perform a detailed compute and memory organizational study to determine how to fit things here. But to go over the sparse convolution engine, we use the tensor block in vector mode and scalar mode. So for vector mode, if you recall, we can perform 6 8-bit multiplications and an accumulate. And then the result of this can be accumulated with the previous result or with the cascade input, which is a dedicated wire from the previous tensor block in the chain, but we cannot do both in the same cycle. And so to map HPIPE to vector mode, we take our existing convolution engine and swap out the DSPs for tensor blocks. This is easier said than done, but it gets us a 3x or up to 3x performance improvement at the cost of lower precision. Sparsity is still supported, so we don't have any restrictions on inputs here like we do in tensor mode, and so we can still support zero-weight skipping, but we do need an external accumulate register, because unlike DSPs, tensor blocks can't cascade and accumulate in the same cycle. And so zooming in here, instead of having this chain of 5 DSP blocks to implement 10 multiplies, we can have just 2 tensor blocks where each tensor block takes up the same amount of area on chip as a DSP. And we have 2 multipliers unused here, as we have 12 total multipliers. And then here we have our accumulate implemented in soft logic outside of the tensor block chain, rather than inside the last tensor block in the chain like up here. Scalar mode can perform 3 independent 8-bit multiplications. And similar to vector mode, we can either accumulate with the previous register result or with the cascade input. But in this case, we have 3 different cascade inputs as we're producing 3 independent outputs. So depthwise convolutions map to scalar mode in our case. If you recall, for depthwise convolutions, we essentially have it so that we apply a single filter to each input channel so that the number of output channels is the same as the number of input channels. And each one of these filters has a depth of 1, meaning the maximum input channel parallelism must also be 1. And so what this essentially boils down to in hardware, it means that we're only using 1 multiplier in each tensor block if we were to use vector mode, for example. This is very inefficient. So for 3 dot product engines, we're not using the vast majority of multipliers shown here. And so we can use scalar mode to more effectively pack these multipliers on the Stratix 10 NX. And so rather than having these 3 separate multipliers here forming 3 separate dot product engines, we have this all combined into one tensor block in scalar mode as shown here. So a reduction in area of up to 3x. So next, jumping into the compute and memory organizational study, and this was used primarily for the dense convolution engine. So to recall, the tensor block in tensor mode has 30 total 8-bit multipliers. Block floating point can also be used, which we'll cover later in the presentation, and we're operating in vectors of size 10. And this is the main limitation that we'll see, which prevents us from implementing regular sparsity. So where sparsity would need to be in blocks of size 10 rather than just sort of unstructured sparsity. And so half of these, half the data has to be preloaded into a set of ping-pong registers, which hide the loading latency. So while we're preloading one set of register, we can use the other set for computations if it was already preloaded earlier. And then we broadcast in a set of 10 values, so a vector of 10 values against all 3 preloaded vectors. Similar to the other modes, we have some dedicated cascade inputs here. One new cascade input is a cascade input here, which we'll use for preloading, as we'll see shortly. We have 3 different preloading methods in tensor mode that we can use. So data input mode is the first one. In this mode, we preload values 10 at a time over 3 cycles, and we use almost this entire data input to do it. So we're preloading in 3 vectors at a time through that input into these ping-pong registers shown here. And since we're using this entire input, we can't hide the loading latency with computations. For side input mode, we're preloading in 2 values at a time over 15 cycles. And then so the bottom 80 bits in the data input can be used for computations. So 10 total values there that can be used for computations, while the last 2 are being used to preload. And so we can hide the loading latency despite it taking longer than data input mode. Lastly is cascade mode. So cascade mode is a bit different in the sense that we are using this cascade load input to preload values 10 at a time over 3 cycles, but the total loading latency depends on the length of our cascade chain. So if we had 3 tensor blocks essentially that we were loading into, it would take 9 total cycles. But since we're using this cascade input, the data input can be used for computation, so we can hide that loading latency. There is a caveat here in the sense that we need an extra block at the top of each chain. So that block will be configured to use data input mode. And so it'll receive the values in data input mode. It won't do any computations, but it'll send those values down the chain out the cascade load wire shown here and down into the rest of the chain. And so that extra block increases the area, and that also increases the loading latency by an extra 3 cycles. So the question becomes, what is the best preloading method, and should we preload waits or activations? So we did a performance analysis to determine this. We didn't look at data input mode as there's no way to hide the loading latency, but we looked at cascade mode in C and side input mode in S, and we looked at preloading waits versus preloading activations. And this is compared to a baseline design with DSPs that has no preloading. So with preloading waits, we found that we end up getting a lot of stalls, and this is because we can only hide the loading latency if we have larger output widths. But for the majority of networks, the output width decreases as we go deeper and deeper into the network, and we can't hide that loading latency. And so for activations, we found that we don't have any stalls, at least in the mobile nets, and that's because we can hide the loading latency with larger numbers of output channels, and the number of output channels increases as we go deeper and deeper in the network. And so we decided to go with preloading activations. Between cascade mode and side input mode, we didn't find any raw performance differences in terms of cycle count. However, in terms of frequency, we determined that cascade mode would likely allow us to achieve a higher maximum frequency, as we would only have a memory beside the top block in each chain, rather than multiple smaller memories beside each block as in side input mode. On the right here, we have a memory analysis. And so between the different implementations, we looked at how many MLabs we would need for the activation buffer. We also did one for the wait buffer, but we're just focusing on the activation buffer here. So here's our baseline with no preloading. With preloading waits, it spikes up for both side input and cascade preloading. And this is because we need an activation beside each tensor block in the chain now. Whereas for preloading activations, this is a lot lower, as shown here. And so this confirms our choice to go with preloading activations, as MLabs actually ended up being one of the main limiting factors for vector mode when we went to higher parallelism settings. And so we did want to decrease this as much as possible. Sparsity support. So I mentioned that in tensor mode, sparsity has to be in blocks of 10 weights. So the question becomes, how much of the sparsity do we have in networks? For the mobile nets, it's relatively low. So it's 0.04% overall. The majority of the sparsity is in earlier layers, but these earlier layers make up the fewest amount of computations in the network. For Resnet 50, which we trained to have 85% regular sparsity, there was only about 20% block sparsity. So the conclusion was that it's not worth it to include sparsity support without some sort of specialized training, and that specialized training was outside the scope of this work. So next, I'm going to cover the dense convolution engine. So here's an overview of the dense convolution engine. I'm just going to go through the data flow rather than jumping into what each module does and overwhelming you with information. So we have our input activations. So these are the results from the previous layer. Those get sent to the tensor activation buffer, where we store them until we have enough of them to start the preloading process. Once we can start the preloading process, we'll just follow this wire into the dot product engine. It will go into the top tensor block in the chain, and it will be cascaded down the chain as shown here. This top tensor block isn't used for any computations. As I mentioned, it's configured to use data input mode to cascade the values down the chain. These other two blocks use cascade preloading. And so once we've preloaded all our values here, we can start broadcasting in values from the memories. We have multiple copies of the memories for timing reasons, but following this brown wire here, you'll see it feeds into the second and third block in the tensor block chain. And then we send those values into the dot product engine. We do the computations, so our 10 multiplications, accumulate the results, send them down the chain, accumulate them here as well, and then output them here. This output will go into the tensor output buffer. So this is a new module we need. Since we want to reuse our preloaded values as much as possible, it means we're not computing complete outputs. And so we can't just accumulate them in a register. We have to store them in a memory and accumulate them that way. And so once we've computed the final value, we can output that and send it to the next layer in the neural network. Another thing we implemented was block floating point support. This was in an attempt to increase our accuracy on the Stratix 10NX. So block floating point shares one exponent between 10 values on the Stratix 10NX, so one 8-bit exponent between 10 8-bit values. In the picture here, we have one exponent shared between 5 values. That's just because I couldn't fit 10 values in the image, but on the Stratix 10NX, it's shared between 10 values. And so what this means is that ideally we'd get a higher accuracy when using block floating point. But for best hardware efficiency, we want to have our dot product across input channels. But different channels are usually not very correlated in magnitude for the shared exponent. So the way the shared exponent works is we take the maximum shared exponent and then align all the other values accordingly. And so if these other values are from different input channels, it's possible they're not very correlated and we're losing information. And so that's one potential issue here. And so what we found with block floating point support was that our top 5 accuracy drops by about 1% in the best case. Block floating point is intended to help accuracy, but it needs a combination of smart training or a floating point based pipeline, as we also lost some accuracy when converting from fixed point to floating point, as HPIPE currently only supports fixed point for the majority of layers. The minimum logic usage also spiked up. So this is the minimum amount of logic we would need to implement a network on the FPGA. So this is the slowest implementation possible with the least amount of multipliers. And we're now using 71% ALM usage due to all these extra converters, which does not bode well for higher parallelism settings. And so these extra converters are a fixed point to 16-bit floating point converter, 16-bit floating point to block floating point converter for the tensor blocks. And then the tensor block output is actually 24-bit floating point. So we need to convert that back to fixed point before sending it to the rest of HPIPE. Now, we could certainly implement floating point support for the rest of HPIPE to reduce this area increase here, but then we would have area increase in other layers. For example, a bias add layer, which only does an integer add right now, would have to be modified to do a floating point add, which uses a lot more area compared to an integer add. And so there's no easy solution here. So another change we had to do was we had to implement tensor mode support for Depthwise convolutions. And this is because scalar mode does not support block floating point. So we used scalar mode, if you recall, for Depthwise convolutions, which did 3 independent multiplies. But without block floating point support, we need to use tensor mode support, which is not ideal for 2 reasons. One, it increases area by about 1.5 times, as we need to increase the number of tensor blocks used. And 2, it adds some additional complexity, as we'll see on this slide. So here I have an example depthwise convolution. So recall that for a depthwise convolution, each filter is essentially only has a depth of 1. And so this input channel here from the input activations will correspond with this filter and with this output. This blue one here, so the second input channel will correspond with this filter and this output. So there's no correlation between the different input channels. And so what this essentially means for tensor mode is that it causes some complications when we want to reuse as much preloaded data as possible. So our preloaded data would look like this. So we'd preload every one of these filters shown here, but there's no correlation between these filters. So we don't want to accumulate these filters together. Whereas on the tensor block, these dot product engines will do that accumulation after the multiplication. And so what this essentially boils down to is we need to set all the values to 0 except one of them. And so this F1 will just correspond with this one and will not accumulate with any of these filters shown here. And we'll do that for each different cycle shown here. And so this adds some additional complexity. And again, it means we're underutilizing the multipliers. So we're only using 1 multiplier in each dot product engine in every cycle. So next, I'll go over our results. First is cycle count simulation results. So vector mode comes close to its peak performance improvement of 3x. So in this graph here, we're looking at throughput at 350 megahertz. The number of tensor blocks targeted is in brackets, and this was chosen just to be able to route at least 350 megahertz while achieving the maximum performance possible. And so when comparing the DSP implementation to the vector mode implementation, we're close to our peak performance improvement of 3x based on the number of multipliers. Tensor mode, shown in green, falls short of its peak performance improvement of 15x, but still provides good speedups. And this is for 2 main reasons. One, we have those unused tensor blocks at the top of the chains, which are used for the preloading process. And 2, depthwise convolutions use only 3 out of 30 multipliers, regardless of if we implement them with scalar mode or tensor mode. And so we're heavily underutilizing multipliers for all those layers there. FPGA results. So takeaway here is that we got a lower frequency due to the larger bus sizes. So we have these large vectors that we need to route between the tensor blocks, and this puts a lot of pressure on the routing fabric. And so for MobileNet v1, for example, we have a drop of about 100 megahertz when going from a DSP-based design to a tensor block-based design, and this increases to about 200 megahertz for MobileNet v2. And so our results here are lower overall than the raw performance from the previous cycle, but we still get good speedups compared to the DSP-based design just due to all the extra multipliers we have. Some area results. So baseline design is shown here, and then you'll see that for vector mode and tensor mode, we have large increases in area, some cases up to 94%, and this is another reason for that big frequency drop we see down here. And this big area usage is actually after we performed a bunch of optimizations to reduce it by combining memories and limiting logic duplication. And so there's just a lot of pressure on the routing fabric and registers on the FPGA to achieve this higher tensor block count. Comparison to prior work. So in terms of Stratix 10NX, there's no other CNN accelerators that we knew of when publishing the thesis. Andrew Bertros's NPU for RNNs achieves 3.5 times better performance improvements when switching to the NX compared to their baseline design, whereas we achieve 7.1x performance improvements compared to our baseline design. But our accelerator is also more specialized for each layer in the neural network compared to theirs, which is a processing element-based accelerator. Other other FPGA accelerators we compared to, we have anywhere from 4.7 to 28 times higher performance in the thesis. And for GPUs, we have 6.2 to 17x speed up for a batch size of 1 and 1.3 times speed up for a batch size of 128 on the AI-optimized NVIDIA V100. And especially for this batch size of 128, this is where GPUs have typically outperformed FPGAs in the past. So the fact that we can still beat them here despite having a smaller die size and using a lot less power was a pretty good surprise. Another AI-optimized FPGA is the Xilinx Versal. So this is a 7 nanometer AI-optimized FPGA, so smaller process node than the Stratix 10NX. Here we have 400 AI engine tiles with a peak frequency of 1.3 gigahertz. These are separate from the programmable routing fabrics. They still have DSP blocks present, and they have both a 512-bit SIMD vector processor in addition to a scalar processor shown here. They have shareable memory between the different AI engine tiles, and they have additional features for computer vision like hard logic video decoders. And so we found one prior work on the Xilinx Versal, and in this work, they get close to 3,500 images per second on MobileNet V1 SSD. The authors don't mention their DSP usage, but they do say they're using all the AI engines on chip. And so since the SSD variant of MobileNet V1 has about 2 times higher operations than the base version, which we use, we scale up the results linearly by 2x. And despite that, we still achieve 4.0 times higher throughput than their implementation. And we're running at a much lower frequency than these AI engines and on a larger process node as well. So just some architectural recommendations before finishing off. So one of them is increasing multiplier density for scalar mode. So we found that scalar mode was the limiting factor preventing us from reaching that 15x performance improvement for our tensor mode, as Depthwise convolutions make up a big portion of the calculations in the networks we tested. And so having scalar mode support, say up to 6 multiplications instead of 3 at a reduced precision, could be helpful in further increasing performance. Support for larger multiplication sizes. So I didn't talk about this much, but mean layers, which are present in the mobile nets, require these larger multipliers, which we currently implement using 7 tensor blocks. And so while these mobile nets don't have a lot of these mean layers or require these larger multipliers, this could potentially be an issue for other networks. And so having some support for these larger multiplications would help these other networks as well as help other applications on these devices. 2 recommendations for block floating point support. So having block floating point support in scalar mode would be helpful, as we currently have to switch to tensor mode for block floating point Depthwise convolutions. And then having some dedicated block floating point converters or IPs would help, as the soft logic converters for just going from floating point to block floating point, which any design will need to implement, increases the per layer area by about 1.26x. And so having some dedicated converters or IPs would help reduce this area increase. So in conclusion, tensor blocks can be exploited well for convolutions, but we need to use multiple modes. So scalar mode is used to pack 3 Depthwise convolutions, except for block floating point, where we use tensor mode. Vector mode supports sparsity and provides simulation speedups of up to 3x. Tensor mode does not support sparsity, but provides simulation speedups of up to 8x. Quantizing to 8-bit causes a bit of a drop in accuracy, but there's still an open question here. Can we get better accuracy improvements with proper block floating point support? FPGA frequencies are lower than standard DSP blocks, but we still have speedups of up to 7.1x. Some low-cost architecture changes could improve performance. And our paper was accepted at FPD 2022. Our presentation will be next Tuesday, our time, or next Wednesday, Hong Kong time. Future work, supporting more CNN layer types so we can support other types of networks, improved TensorFlow training, so I touched upon this earlier, improved 8-bit fixed point quantization so we can more accurately model the hardware, specialized training for block floating point support or general floating point support for the remaining HPIPE layers to improve our accuracy when using block floating point, block sparsity aware training. So rather than having unstructured sparsity, having something with structured sparsity means we can now support sparsity in tensor mode and decrease area usage and increase performance. And then HBM support for storing weights off chip. So we can't fit larger networks like Resnet 50 right now. So having HBM support could help us in fitting those larger networks on the Stratix 10NX. And then multiple FPGA support. So this would be combining the Stratix 10NX work with Mohammed Ibrahim's thesis work to support multiple NX chips. And then some Crossroads related future work. So evaluating the Crossroads architectural enhancements in relation to HPIPE. So leveraging the network on chip, the base die, compute units, memory, etc. So looking at how we can leverage that for HPIPE is some future work for Crossroads. And so that concludes the seminar.